Hello everyone, welcome back to my channel. So today we would be learning about the semiconductors, and we have already learned about the intrinsic semiconductors. We would be looking upon what is extrinsic semiconductors, what is doping, and what are p-type or n-type semiconductors. So without further ado, let's get started. So if I talk about doping, so what doping is basically, we have already seen that in many sports areas there are sports persons who try to make their performance better by using some certain sort of external resources, by injecting themselves with certain injections that in many international platforms, Olympics and Asian Games and Paralympics, whatever, there are different sort of sporting events that take place, whether they are national or international. It is completely prohibited, strictly prohibited. Although they sometimes use unfair practices, it causes like a sort of chemical reaction that basically increases the performance while they are in the game, and it is an unfair means due to which they might get advantage of. That is why it is completely prohibited. Now, just like how in the sports people use it, people use an external resource for their own betterment, for their own advantage. In physics also, okay, let me drink some water. So sorry, I was really parched. Now moving on, just like how in physics we do use this entire concept for the betterment of us. We are introducing some external resources in our previously intrinsic pure semiconductors for our own advantage. What is the advantage here? The advantage is that we would be increasing the conductivity of our semiconductor, because just like how we all know that intrinsic semiconductor, they are completely you can say useless in itself. Not useless, they are useful if I talk about certain situations. But if I talk about semiconductors in today's date, it is present in almost every technical item that we use daily in our daily to daily lives, whether it is our phones, whether it is our laptops, whether it is our any sort of technical or electronic device that we use, it has semiconductors within it. Now we all know that phones are used by someone who lives in South Africa, and it is used by someone who lives in Denmark, it is used by someone who lives in India. So it is used by everyone. It doesn't matter what the temperature is at that certain place, and at that particular time the technical items, they work completely fine. So but that shouldn't have been the case if we used intrinsic semiconductor, because we all know that intrinsic semiconductor at temperature 0 Kelvin, or if in lower temperature, they start to act like insulators. Why? Because their conduction band is completely empty, their valence band is completely filled at 0 Kelvin, and at relatively lower temperatures the conductivity is still less, not how much we want it to be. Therefore, in order to solve this certain problem, in order to make the semiconductors much more practical, right, we introduced this extrinsic semiconductor, and we introduced this process called doping. Doping is nothing but, let's read the definition: the process of deliberate addition of desirable impurity to a pure semiconductor so as to increase its conductivity is called doping. When we are introducing some external impurity atoms to my semiconductor lattice in order to increase its conductivity, right? Let me repeat it. When I am introducing some external impurity atom to my previously intrinsic pure semiconductor in order to increase its conductivity, this process is known as doping. And the impurity atom that I would be adding in my crystal lattice, that would be known as dopant, right? We call that dopant. Now, extrinsics or doped semiconductor. The semiconductor doped with impurity atoms are called extrinsic semiconductors. Those semiconductors that are doped with impurity atoms, that these are only known as extrinsic semiconductor. Means that is why intrinsic semiconductor are known as pure semiconductor, because we are not adding any external contaminant to it, and when we do add it, it becomes extrinsic semiconductor. Now, this extrinsic semiconductor is basically of two types, that is N-type and P-type, and both of them do contain impurity, but they are different kind of impurity. Okay, now first let's read about the N-type semiconductor. This semiconductor is obtained by doping tetravalent semiconductors, silicon or germanium, with pentavalent impurities such as arsenic, phosphorus of group 5 of the periodic table. We all know that the silicon or germanium, they belong to group number 14 in the periodic table, and they have a tetravalent they are known as tetravalent. Why? Because the valency is 4. We all know what is valency. Valency is the number of valence shell, valence electrons. Means what is valence shell? The last shell of an atom. And the number of electrons present in that particular cell, they are known as the valence electrons. And what is valency? Valency is the number of electrons that is required to either gain. If I am writing plus 4, then I require 4 electrons to complete my octet. And if I write, suppose any has plus minus 4, okay, it could be minus 2, it could be something else. So if I'm writing minus 4 is my valency, means I have to lose 4 electrons to complete my octet. Okay, so this is how valency works. So tetravalent semiconductors, silicon or germanium, they are tetravalent in nature, means they have a valency of plus 4, means they require 4 electrons. Just like how we see that this silicon, suppose this is a silicon atom, it has 4 electrons in its valence shell. I am only drawing the valence shell. Now it requires 4 more, so what it does is it forms a covalent bond with its neighboring silicon atoms. And we all know what is covalent bond. It is the sharing of electrons. In ionic bond, there is transfer of ions, but here it is sharing of electrons. So just like how you see this silicon atom has completed its octet, so just like that it does so in the case of intrinsic semiconductors. But here my motive is to make my electrons free, right? But here it is sharing and it is completing its octet. So why some electron will lose its bond? Why will they break the bond if they are completely stable? If I am saying that any atoms is completely stable, means they don't have energy, and if they don't have energy, they won't be able to break the bond from the valence band and move to the conduction band. So they have to break the bond, right? And for that they have to gain energy. So what we do is we add a pentavalent atom. What is pentavalent? Just like tetra stands for plus 4, the pentavalent stands for plus 5. So we are adding such atoms whose valency is plus 5, means they have 5 electrons. Let me write it for you. They have 5 electrons in the valence shell, and its example are, you might want to learn or memorize 2 of them for the example if it is asked anywhere. Let's just learn phosphorus, or we can learn arsenic, phosphorus. Okay, they belong in group 5 of periodic table, and they have pentavalent valence, means they have plus 5 valency. When pentavalent impurity atom is added to pure semiconductor, then 4 electrons of arsenic participate in bond formation. 1 electron remains extra on it. Addition of large number of arsenic atoms, large number of such electrons are obtained, and they lie in a level called as donor level. which is very close to the conduction band. So without let's first understand what actually happens. Suppose this is a germanium lattice. These are my germanium atoms, and in that I have externally doped one arsenic atom. Now we all know that it has five electrons. So before, like how I said, they require only 4 electrons to form the covalent bond. Now there is one extra electron that remains unbonded or is very weakly bonded to my arsenic atom, and it could be easily freed just by providing only a small amount of energy, and it would be easily be able to jump from from the from the valence band to the conduction band. Now this electron becomes one another free electron. This becomes a free electron, and because this certain pentavalent atom has given one free electron, that is why this is known as the donor atom, or you can say the donor electron. Okay, because it has donated one electron. And this donor electron, when we make the energy band diagram of n-type semiconductor, we make one another level. We know that different levels, when they are very close to each other, they form a band, right? Now but here it is only a level which is closer to my conduction band. You see, this is my conduction band, this is my valence band, and this level, this donor level, is very close to my conduction band. Means if my electron is able to jump to the donor level, they are easily able to jump to my conduction band. So their difference is only 0.01 electron volt. So this helps my more electrons to jump from my valence band to the conduction band. So got the entire here. Now here, since there are number of electrons is greater, right? Here it is not like how in the intrinsic semiconductor we saw that in the case of intrinsic or pure semiconductors, the number of electrons in that one, the number of electrons is equal to the number of holes. Why? Because the number of electrons that moved from the valence band to conduction band, only they created vacant places, and only at those places one effective positive charge came to existence, and they were known as holes. But here what we are seeing is that there is already, without any movement of any electron, there is already one extra electron present. So that is why here automatically, if we add even within 1000 within 1000 something, if we add within 1000 germanium atoms, we add one or two arsenic atoms or phosphorus atoms, we will see that there is still total amount of free electrons in the conduction band is still increasing, right? So here automatically the density of electrons to that of holes becomes more or greater. Therefore in here the electrons are known as the majority charge carriers. They are known as the majority charge carriers in n-type semiconductor. Charge carriers, how will we remember it? N for negative and electron has negative charge. That is why here who is the majority carrier? Electrons. And holes here becomes the minority carrier. They are known as the minority carrier or minority charge carriers. Thank you so much for hearing me till now. We will move to the p-type semiconductor in my next video. Thank you so much. Radhe Radhe.